What if I told you that the entire field of calculus, the math behind everything from rockets to stock markets, rests on one simple idea? An idea so powerful that it changed the whole world forever. Calculus is the language of change, and at its core is the first principle of differentiation. This principle is the foundation of all derivatives, and today we're going to explore who invented it and why it works, and how you can use it to solve problems. Before we get into the math, let's take a quick trip back in time. Calculus was independently developed by two giants of mathematics, Isaac Newton and Gottfried Wilhelm Leibniz. But the idea of first principle was actually inspired by earlier thinkers like Archimedes, who used similar ideas to calculate areas and slopes or gradients. Newton and Leibniz took these ideas and formalized them into the calculus we know today. Here's the fun fact. Newton and Leibniz had a huge issue around who invented calculus first. Well, Newton claimed that he came up with it first, but Leibniz published his work earlier. Anyway, today we credit both of them for laying the groundwork for modern mathematics. Their work revolutionized science and engineering, and it all started with the first principle of differentiation. Okay then, so what's the first principle? Well, at its core, it's all about finding the slope of a curve at a single point. But here's the problem. Slopes are easy to calculate for straight lines, but curves are, well, curvy, right? So how are we gonna do it? Imagine if you are driving a car and your speedometer is broken. To find the speed at a specific moment, you could maybe measure how far you have traveled over a period of time and find a rate, which is to do distance divided by time. But that also has the problem, because the further you go, perhaps the more variation of the speed at which the car is traveling at. So how do we do that more accurately? Well, you could measure how far you go over a smaller and smaller time interval. And the smaller the time interval is, the more accurately you can capture the speed. Well, first principle does exactly that. But for slopes, not necessarily for speed. Now we're going to have a look at how it works mathematically. Well, let's say I have some random curve, right? We want to find the gradient at this particular yellow point. For the argument's sake, we call it point x here with the x coordinate. So earlier on, you would have to maybe grab another point after that, which has another x coordinate, where I make it here, h distance further from the previous point. So the x coordinate of this will be x plus h. So to capture the gradient at this particular point, we take these two selected points and draw a line between them. And basically to find the slope or the gradient of this yellow line, we just do rise over run. Or some people may know it as delta y over delta x. That is effectively to find how much y changes when x increases by a unit. So let's put that into the math. Well, though we already know the x values of these points, but what are actually the y values? Well, for the argument's sake, we would describe the curve by a function of x like this. So the y values of these 2 points are basically just put the x values into the function, which can be any function, right? Whatever that comes to be, that will be the y values. If we put x plus h into the function, the notation to do that is to do f in parentheses x plus h. Similarly, for the x coordinate, the corresponding y value would be f of x, because we put x into the fx. Because we want to do delta y over delta x. So delta y would be just the rise between the 2 points. So this will be the upper point minus the lower point. So fx plus h minus fx, which will be the little distance here. And the delta x, or the run in this case, would be just x plus h minus x, which logically gives us the h distance that we made up earlier. So delta y over delta x will give us that rise, which is this expression here, divided by the run, or the delta x, which is just h. That is quite simple, right? But here's the problem. As you can see, perhaps the best way to illustrate visually what would be the slope at a point would be to draw what's called a tangent. So I'm drawing a tangent, presumably at the point x here. And apparently the slope of the green line, so-called tangent, is not quite the same as that of the yellow line. So we have a problem. And here's the key idea. In order to make the gradient of the yellow line as close as that of the green line, we need to decrease the distance h. So I'm just gonna illustrate how decreasing the distance h makes the slope more accurate. So again, let's say I start with this. When I decrease the horizontal distance, this point will go down along the slope like that, slowly. And as you can see, as it goes down, the slope of the yellow line becomes closer and closer to the slope of the green line until it's so small so that the difference between the two slopes very small. Well, how do we do that mathematically? We gotta make this h very small, approaching zero technically. And that is a very key idea here in the first principle of differentiation. But to write that more appropriately, instead of using delta y over delta x, we call it dy over dx. So the d here means that we are talking about differential calculus, where we are taking very small changes for y and x to capture the exact value of the slope. But again, that is only possible when we say that h is going very small. And in mathematics, we use the language of limits here, where h approaches zero. Well, that thing is tagging along with some reasons. Now let me show you how it works exactly. So I'm just gonna put our first principle equation around here. So let's differentiate a function fx, which is defined by x squared. So if we follow that first principle, we're gonna have f of x plus h to be equal to x plus h squared. Well, I know seeing a lot of letters might make this less appealing, but I hope if you stick with me, you're gonna be fine. So what we need to do next? Well, we just put them into the formula. So I'm not gonna write the limit of h approaching zero yet, just to keep it clean. So I have the function of x plus h. I have x plus h squared minus f of x. So it's just x squared there by the definition. And then all divided by h. Of course, in order to simplify this, you need to expand the first term. But you can follow along by just doing x plus h times x plus h and just do the expansion. I hope that makes sense to you. But I'm just gonna write the result. We're gonna get x squared plus 2hx plus h squared, and then don't forget the minus x after everything. Still all divided by h. As we can see, the x squared terms cancel here. So that leaves us with 2hx plus h squared, all divided by h. We can see that h is a common factor in the numerator part. So we get h, and in parentheses we have 2x plus h divided by h again. Again, you can see that the h here and the h here cancel. So we only have 2x plus h. We shouldn't forget that we take the limit of this whole thing when h approaches 0. And when h approaches 0, whatever the 2x is, h will be very small or too small. And we call that negligible, which will be disregarded or ignored. And that leaves the whole thing with just 2x. That means we can finalize up here that the derivative of x squared is just 2x from first principle. Now, of course, you don't need to do this every time you differentiate a function because there are already useful formulae for you to use. But this is the first principle. And this is actually what gives rise to all the formulae that you have learned, which looks like one of these. So why does first principle matter? It's not just a neat trick, it's the foundation of all differentiation rules. Every formula you learn in calculus, from the power rule to the chain rule, is all derived from this key idea. Now, if you have made it this far, I've got a challenge for you. Can you use the first principle to differentiate a function like this? Try it out and let me know your answer in the comments. If you haven't seen other videos that I have made on differentiation, I have also made some basic videos about the key rules in differentiation that would allow you to differentiate any kind of function. And if you enjoyed this video, please like and subscribe. And don't forget guys, keep studying. Bye.